Now, what we're working on right now will be Bernoulli's principle. Bernoulli's principle explains how pressure can change in a pipe whenever you go from a large volume to a smaller volume, or a large area to a smaller area in the pipe. And we look at the pipe like this. Let's just say that we have a pipe that has a small area up top, and it comes down to a larger area at the bottom. And this pipe, the water is going to flow up like this to this area. So we'll have the direction of the flow this way. Now, we're going to call this area 1. Let's make the 1 a subscript. The area 1 is the area of the pipe here, and this will be area 2, the area of that pipe there. So that area 1 is greater than area 2. Here, you have a pressure, the pressure of the liquid inside of the pipe that we call P1, and up here, the pressure of the pipe we call P2. Now, the fluid is going to flow through the pipe in this section with a velocity V1, and it's going to come out of this end of the pipe with a velocity V2. We're going to look at the same volume of liquid through here compared to the same volume of liquid up here. Now, that means that a small delta L, we call this delta L1, is going to be moving through this part of the pipe, and that would be equal to a thicker section of delta L through this pipe. So we call this delta L2. All right. Now, these pipes are also at different heights. We're going to call the heights Y1 and Y2. So coming from the midpoint down to the ground, we draw that out, and we'll say this is Y1. And coming from the midpoint down, we will call this Y2. So we have delta L is the change in length for the distance that the liquid is going to flow that way. Delta L2 is that length. We have two areas, the pressure and the velocity. Now, let's look at the work that it takes to push this liquid through the pipe. We know that work is equal to force times distance. We know that force is equal to mass times acceleration. We know that pressure is equal to force divided by area. And so force is equal to pressure times area. Now, if we take, we have pressure, we want work in terms of pressure. So we substitute force, we substitute pressure times area in for force in the work equation. So we have the work is equal to pressure times area times distance. Now, our distance is delta L1 for here, and our pressure is P1. Our area is A1. So this is going to become work, the work done in the first section of the pipe is equal to the pressure in the first section of the pipe times that area times delta L1. All right? Now, the work in the second section of the pipe up top is going to be called work 2, and that's equal to pressure times area times distance as well. So that will be pressure 2 times area 2 times delta L2. But this is the difference. This liquid has to be pushed. So this liquid does negative work on the liquid that's coming before it. So we put a negative sign to stand for the direction of the force, the work that's being done. Work is force times distance. This fluid is doing negative work against the fluid that's trying to push it up. Now, we have a third work that's dependent upon gravitational potential energy. This work 3, is equal to mass times gravity times height. Now, this fluid is being pushed up from this height Y1 up to a height Y2. So this height, this will be mass times gravity, and the height is going to be Y2 minus Y1. Okay, and now we move to the other part of the board for more space. The work total is equal to the work 1 plus work 2 plus work 3. So we add our 3 work equations together to get the total work on this object. Work 1 is equal to P1 A1 delta L1. Now that's minus, it's really plus a negative work 2, that's P2, A2, delta L2. And then since gravity, you're having to act against gravity going up, that's going to be equal to minus mass times gravity, Y2 minus Y1. Now, work is also a form of kinetic energy. And work is equal to the change in kinetic energy. Our kinetic energy is equal to 1/2 mass times velocity squared. But you have a V1 and a V2. So kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared. So we have this kinetic energy here, 1/2 mass times velocity 2 squared minus 1/2 mass times velocity 1 squared. Now, this is the total work that is performed to move the fluid from one location to the next with two different velocities. Now, we set these two equations equal to each other. If work is equal to this and work is also equal to this, then 1/2 mass times velocity 2 squared minus 1/2 mass times velocity 1 squared is equal to pressure 1, area 1, delta L1 minus pressure 2, area 2, delta L2 minus mass times gravity. I'm going to go ahead and distribute this through to get two terms. Mass times gravity times Y2 plus mass times gravity times Y1. Now, we have a mass in 4 of the terms, and we want to get rid of that mass, so we're going to make a substitution. We know that, going here, density is equal to mass over volume. So mass is equal to the density of a fluid times volume. Now we're going to use density 1 and density 2 right now because we're going to call this area 1 and area 2. Volume, we know, is equal to area times change in length. So we're going to make that substitution here. Mass is equal to density times area times change in length. So every time we see a mass, we're going to call it rho A delta L with the subscript 2 or 1. So this becomes 1/2 rho 1 A1 delta L, this is 2, V2. Rho 2 A2 delta L2 V2 squared minus 1/2. This mass is 1, so that's going to be rho 1 A1 delta L1 V1 squared equal to pressure 1 A1 delta L1 minus pressure 2 A2 delta L2 minus. Now, a mass here, that's going to be the second part, so that's going to be rho 2 A2 delta L2 G Y2 plus rho 2 A2 delta L2 G1. This is all 1. 1, 1, 1, Y1. All right. Now we look at this. We stated earlier that the volume of fluid here is equal to the volume of fluid here. That means that volume 1 is equal to volume 2. So A1 delta L1 has to be equal to A2 delta L2. So the volumes have to be equal. A2 delta L2, A1 delta L1, A1 delta L1, A2 delta L2, A2 delta L2, A1 delta L1. Every single term has an area times a length in it. So every term has a volume in it, and those volumes are all equal. So if you divide by those, they all cancel. Now let's simplify this equation. We have 1/2 rho 2 V2 squared minus 1/2 rho 1 V1 squared is equal to pressure 1 minus pressure 2 minus rho 2 G Y2 plus rho 1 G Y1. All right, now we're close to the final form of this equation. The only thing we need to do is I want all 1 subscript terms on the left and all 2 subscript terms on the right. So I'm going to subtract P1 to the other side. Negative P1 minus 1/2 rho 1 V1 squared minus rho 1 GY1 is equal to negative P2 minus 1/2 rho 2 V2 squared minus rho 2 GY2. Okay, now, again, every term has a negative sign in it, so I'm going to divide through by -1 and rewrite the equation. So P1 plus 1/2 rho. I'm also going to take off the subscripts for the rho 1 and rho 2. The density of the fluid we're going to consider to be an ideal fluid, so it doesn't compress significantly when you go from one part of the pipe to another. So rho 1 is equal to rho 2. We're just going to substitute that for rho and leave off the subscript. That means we have velocity 1 squared minus rho g y1 is equal to, that's plus now, divided everything through by -1, P2 plus 1/2 rho V2 squared plus rho g y2. This is the final form of Bernoulli's equation. This relates the velocity on one side of the pipe to the velocity on the other side of the pipe, the height at one side of the pipe to the height of the other side of the pipe, and the two pressures that are going to be measured at both parts of the pipe.